detecting them, and observe datasets with deepfake audio and metrics to evaluating the deepfake audio detection models. Based on that, I will define the aim of the research and the questions that need to be answered. Further, I will focus on possible solutions for improving the generalization capabilities of deepfake audio detection and show experimental results. At the end, I will give some conclusive remarks, define future works, and give answer to the reviewer questions. Deepfake audio has transformative potential in entertainment, enabling seamless dubbing and voice acting, and in assistive technology, enhancing communication device usability for individuals with speech challenges. However, the technology also poses serious threats such as misinformation and identity theft, or create compromising or incriminating recordings of individuals, which can then be used for blackmail or extortion purposes. All these dangers highlight the need for robust machine learning countermeasures. Existing mainstream studies on audio deepfake detection can be broadly categorized into two types of solutions. First is pipeline approaches, and second is end-to-end detectors. Pipeline approaches involve a two-step process with a front-end feature extractor capturing relevant audio features, and a back-end classifier making the final detection decision. On the other hand, end-to-end detectors aim to learn the detection task in a single step, leveraging deep neural networks to map raw audio data directly to the detection decision. Recent advancements in this area include integrated pre-trained models like WAV2VEC, Hubert, or Whisper into future extraction models of pipeline detectors, and utilizing various deep learning algorithms presented on the slide. For back-end classification, showcasing the adaptability and robustness of deep learning in deepfake audio detection. Machine learning algorithms' ability to distinguish real from fake audio relies on diverse real-life training data. The pros and cons of the datasets used in this work provided on the slide. Early datasets were vital for improving automatic speech verification system security. The ASV spoof challenge has furthered this by focusing on detecting various attacks, including deepfakes. However, these datasets lack real-world scenario representation, impacting model performance. To address this, researchers have collected an in the wild dataset in real-world conditions comprising audio deepfakes for public figures and politicians. Additionally, other datasets like the fake or real or fake have been developed, each with its advantages and limitations shown on the slide. To evaluate the performance of deepfake audio classifiers, we plan to use the equal error rate metric, which is defined as an error rate at a particular special operating point at which the false alarm and miss rates are equal. The lower result means better performance. Taking into account the current state of deepfake audio detection field, we can say that the ASV spoof dataset is central to deepfake audio detection because of its size and diversity, with RAVNet 2 emerging as a leading model. However, RAVNet's two limitations in generalization beyond controlled datasets raise concerns about its reliability in the real-world scenarios. Understanding RAVNet's details and enhancing its generalization capabilities are crucial next steps in improving deepfake audio detection. To do this, it is necessary to answer the next question. First is what are specific aspects of RAVNet architecture or training methodology can contribute to its suboptimal generalization on diverse datasets? Second is how do different feature extraction techniques in the first layer of RAVNet impact the model accuracy and generalization capabilities? And the last one is can alternative neural network architectures be identified to improve the accuracy of deepfake audio detection on both as well as spoof evaluation data and datasets obtained in the wild? Now, considering motivation and research goal, I want to provide a possible approach to solution of this problem. As was said earlier, one of the most promising baseline models from ASV spoof is RAVNet 2. Its architecture illustrated on figure 1. RAVNet 2 is fully end-to-end system that operates directly on raw audio waveforms. As feature extraction layer, it uses sync-on filters with different resolutions as shown on the slide. However, the sync-on layer design can limit its ability to capture small scale features efficiently. Acting as fixed bandpass filter, it might miss nuanced characteristics in audio signals, potentially affecting the model's ability to distinguish the real and fake audios. Currently, the model uses sync-on layer with 20 filters. Thus, to improve its performance, firstly, we can vary the number of filters. Second, we can try to find another alternative feature extraction layers. One of such layers can be encoder outputs from self-supervised methods like Huber or WAV2VAC and its multilingual version XLSR and automatic speech recognition systems like Whisper. Also, the possible solution to improve generalization capabilities is to incorporate the wavelet functions to sync-on filters as demonstrated in the figure 2. This integration aims to enhance RAVNet's capacity to distinguish subtle differences between real and fake audio signals. It does so by combining wavelet's variable time frequency resolution with sync-conf's bandpass filtering, leveraging the strength of both techniques. To further enhance RAVNet's generalization capabilities for deepfake audio detection, a two-step training approach can be employed. First, the network is pre-trained on the urban sound dataset, which offer a diverse range of urban sounds excerpts. Subsequently, the pre-trained network is fine-tuned on the target ASV spoof dataset, refining its ability to differentiate between real and fake audio signals. Another approach to enhance RAVNet's performance is the use of augmentation techniques. For example, the RAV boost method, which introduce various types of noise and distortion to RAV audio waveforms to simulate real-world conditions. Additionally, we plan to test the ability the AUCO RASNet model that was created to detect COVID cases based on audios of breath and cough to detect deepfake audios. This design may allow it to capture subtle differences in audio recorders due to its focus on relevant audio features and the use of attention mechanisms. Also, to enhance the deepfake audio detection approach, we plan to use YOLO to analyze the MEL spectrogram, as shown on figure 3, which visually represents the audio data. We aim to combine the spectrogram obtained from the outputs of SynConf filters, as shown on Figure 4, to augment the model generalizability and its capability to adapt to new deepfake techniques. And the final approach we plan to test is the NLP method reformer. It employs a model with positional encoding to capture relationships within the audio data for deepfake detection, achieving state-of-the-art performance on standard benchmarks. This model exhibits the best reported results on established data sets, enhancing our ability to detect deepfake audio signals efficiently. Now let me show the experiment results. The first column on the table on the slide represents the results of the original RAVNet with 20 SynConf filters. Other columns shows the differences in equal error rates between the original model and other proposed solutions. where plus indicates worse results and minus better. Also, both numbers indicates the best results for each data set. The first find is that all suggested approaches demonstrate superior performance compared to the original RAVNet 2 across the in the wild and wave-fake datasets. Second, we partially support the hypothesis that varying the number of RAVNet 2 SynConf filters can enhance deepfake audio detection, but the impact was inconsistent across datasets, indicating that factors beyond SynCon layers, such as dataset characteristics and model architecture, play significant roles in performance. Then RAVNet 2 linked with Whisper showed competitive performance across datasets with relatively low equal errors on all datasets. Thus, Whisper demonstrates strong potential as a future abstraction layer in RAVNet 2 for deepfake audio detection. The network trained with a different combination of wavelet filters demonstrated good generalization capabilities across diverse datasets. Also, the network trained with a combination of sync filters and modeled wavelet showed the second best performance in ASVESPoof data. Augmentation techniques led to improvements in equal error rates across most datasets. For example, in several datasets, augmented data with RAVNet 2 with more wavelet showed lower equal error rates than their non-augmented counterparts. This indicates that augmentation techniques can enhance the generalization capabilities of deepfake audio detection models. In the study comparing YOLO and RAVNet 2 for detect deepfake audio, RAVNet usually perform better, but YOLO, especially when trained on combined spectrograms, outperformed it in some cases. It even topped all models on the real or fake dataset. Despite the benefits of AUKA ResNet provided early, it demonstrated the worst results among the models evaluated in most cases. While its architectures include attention mechanism to focus on relevant features in audio signal to detect COVID cases, it did not perform as well as expected in deepfake audio detection. And finally, the reformer model has shown promising results with lower equal error rates across all datasets, besides the fake or real dataset. As these results indicate that the reform performs well in detecting deepfake audio, showcasing its effectiveness in capture local global dependency for deepfake detection tasks. To sum up, the first research question was what are the specific aspects of RAVNet2 architecture or train methodology can to contribute to its suboptimal generalization on diverse datasets. The obtained results give the answer that the suboptimal generalization of RAVNet2 on diverse dataset could be attributed to its fixed architecture. The silicon layer may not efficiently capture the diverse features presented in real world audio data. Additionally, the training methodology, including the choice of pre-training dataset and fine-tuning strategy, may not sufficiently adapt the model to different acoustic environments and spoofing techniques. To answer the second question is that the network trained with different feature extraction techniques in the first layer of RAVNet as combination of filters demonstrated good generalization capabilities, outperforming the original RAVNet architecture in several datasets. Augmentation techniques led to improvements in equal error rates across most datasets, enhancing the generalization capabilities of the models. Also, using encoder outputs from Huber, Wav, Whisper methods instead of SynConf in RAVNet yielded mixed results with some combinations showing competitive performance, especially in real-world scenarios. And the last one, the answer to the last one question is that experimentation with alternative neural network architectures show potential for improving the accuracy of deepfake audio detection on both ASV spoof evaluation data and datasets obtained in the wild. YOLO showed promise in specific scenarios, outperforming RAVNet2 in datasets like real or fake and wave fake. Notably, the reformer model exhibited impressive results across multiple datasets, showcasing its effectiveness in detecting deepfake audio. Despite this unfortunately, no architecture exhibit exceptional generalization capabilities across all datasets. Therefore, our future work will include first, we suggest retrain RAVNet2 with new data to enhance its generalization performance in diverse and uncontrolled scenarios. Second, conduct additional research to understand factors contributing to varying performance across datasets, such as background noise, audio quality, and diversity of spoofing techniques. Then focus on collecting and annotating new datasets to train RAVNet2 and other models, improving their generalization capabilities. Also, we plan to explore different combination of filters and augmentation techniques to further improve model performance. Consider assembling multiple models and incorporating attention mechanism to enhance their ability and robustness of deepfake audio detection systems. And the last one, we plan to investigate the reformer model architecture and potential enhancements to advance deepfake audio detection technology. From reviewer, I get some suggestions what I should add to my work and some mere remarks to formulation. Also, here some answers to his question. For first one, he asked why we wasn't a deeply investigator foreman, and my answer is that in this work we have only planned deeply investigate RAVNet2. Reformer was used only for comparison. However, as this model showed the best results, we plan explored it in our future work. And second question was a little maybe philosophical, and I want to answer that we also need better deepfake audio detection method that generalize well and can explain why something is flagged. When This perfect synthesis detection is vital to fight misinformation, the protect and protect authenticity. Thank you for your attention. I will be glad to answer to your questions.
Yeah, thank you for your presentation. I have a few questions. The first one, I would like to understand the motivation of using YOLO, the object detector model, for classification. Like, did you created a bounding box annotation for events in the MEL spectrograms, or you did the classification directly using YOLO, or like why YOLO? If you
I
classified it, why not to use?
I understand. As you know, YOLO shows the best results now in computer vision sphere, and I try to create mass spectrograms from my audio datasets, and only use it to classify it to distinguish real and fake audios.
Yeah, I understand, but like if you will go on papers with code or on torch image models where you have results on ImageNet classification, there is no YOLO and it does not perform state-of-the-art results. It's not transformer based or some heavy model for heavy lifting. So why YOLO? Why not like uh, Vision Transformer or Connext or Efficient Net? It's about this.
I understand. Maybe because all my researchers were focused especially on RAVNet 2, and to answer the second question, I need only choose maybe 2 or 3 models to test. Then I choose a YOLO or reformer.
Okay, got it. And I have like small another question. You mentioned sync convolution. Could you like I'm not familiar with this. Could you explain how it works and do we learn something there? Because like I know what is uh sine x on x, like what is the mathematical function behind the sync function, but like what how it performs. Like so what we learned here.
On the input, we have a raw waveform, and then in synconf, as synconf filters, for example, we have 10 filters with a different resolution as shown in the slide. And we try to multiply these functions with different resolutions in with input signals to try to get different nuances characteristics of audio
Yeah.
signal.
I understand this. It's really very familiar with wavelet or time spectrum transformation, whatever. My question is about: do we learn something here if we do just multiplication, scaling, and sliding window? Like, do we have some learnable parameters of syncon filters?
We can learn
Or is
by
just like
parameters. It can be the frequency of this sync
so we learn
functions.
the frequency and scaling coefficient.
Yes.
Okay, got it. Thank you.
Thank you, Juliana. Yes, I have a couple of questions as well. So what is your actual contribution? Seems like you brought several models, architectures, and run them on different data sets. And can you get back to your main table with the results? So probably the preliminary question would be, what are the numbers? So what is this values? Is this error or precision?
It's errors,
Errors.
equal errors
Okay.
of
Okay.
different models.
Yeah. So and yeah. So back to my main question. So what's your contribution? It seems like you got a bunch of different models, trained them on different data sets, and compared them? Anything beyond this?
Uh, First of all, I want to say that all papers that almost all papers that I found in this sphere was about train models on us spoof data set and trying to get best results. But however, all these models show maybe show worse results on other data sets, and then that's why I try to find some architectures with exceptional generalization capabilities among all data sets that it may include different types of attacks or different or for example uh, new spoofing techniques that generate these fake audios. In my researchers, I train all these models only on ASFA spoof data and then test on all other data sets.
Did you bring anything new to these models, to these architectures, like, I don't know, some specifics, some changes in the architecture or whatever?
Yes, if you talk about RAVNet 2, then in first sorry. In first layer, as you can see, there is synconf filters. Uh, First of all, I tried to change the number of filters. Then I tried to use a different feature extraction techniques to see how it may influence on model's performance.
And what are these feature extraction techniques?
For example, it was some self-supervised methods or speech or automatic speech recognition systems, or for example, the syncon filters also add some features from multiplying by labels.
How does it work? I mean, so generally we have artificial neural network, and it, it does automatic feature extraction, correct? And you somehow do something before this, like doing some feature extraction before. Uh,
No, in model, especially.
with some additional layer or what?
No, it wasn't some additional layer. It's architecture of RAVNet 2, and it has first layer of it is syncon filters. And I try to change especially this layer to see how its layer can influence on model performance.
So generally we change activation function, number of neurons, number of layers, number structure of connections. So what was your, so
Uh, uh,
can you bring an example?
for example, if we talk about res blocks, they stay as the
No,
same.
we're talking about sync filters. Is it correct?
Only about sync filters, yes.
Yes. So how do you change them?
No, for example, in RAVNet, there is a synconf with only 20 filters, and I try drop sync filters and, for example, use output from above to back. Above to back model because this model is pre-trained and can um, and can and can
So then the architecture would be like this network without sync filters, but
yes.
before it you have this pre-trained wavenet.
Yes, and in that case, maybe this model become not end-to-end, but pipeline detector.
Yeah, yes,
Because
I see, I understand. And you get from the box this wavenet, or you trained it?
from the box, from Hugging Face.
Okay, so you played with these different architectures, different pipelines,
Yes.
then test it with different data sets
Yes.
and get results.
Yes, the main aim was to see how it may influence on results
Okay,
of
okay, I see.
generalization.
It makes clear. So the second question is about data augmentation. You mentioned it very um, without details, I assume. So what specific technique do you use?
For example, some types of noises,
Yeah, but what type of noises?
white noise.
So how you generate it? Do you have any function description?
Especially this robust method is already implemented, and there is some article about this, and I try to use that techniques that they proposed.
So it's kind of library, or you code it by yourself. So interestingly,
And
so how you do it in practical terms? Because even this data augmentation technique, you have like
for
one
example,
for
during training process, I use some functions with augmentations
what functions?
uh, from this robust method. It's not a library. It only no, from GitHub repository.
So it's a package,
Yes.
and you get some functions from the package and use it for data augmentation
Yes.
techniques. And what is under the hood of these functions? So you mentioned, for instance, white noise. Do you remember the formula for white noise generation?
It's a very tricky question.
Yeah, but it seems like you just bring some different functions, playing with those modules without a deep understanding of what's going on. Okay, fine. And my third question: can you get back to those answers for reviewer? Because his first question, it's a really important one regarding. So you mentioned the he mentioned raw former, and in your thesis, I see this that you mentioned it as well. Whether you added after this first iteration of review,
No, it was there.
but why then you? Because Taras mentioned that it's the best model so far, and you just test without it. You didn't try to change it. Is it correct?
Uh, Yes, Taras mentioned that as this model shows the best results and it's the smaller one, it may be useful to use different feature extraction techniques, especially in Reformer, as I did in RavNet, to test this model. But I need more time for this, not today's
Yes,
after review.
but what he mentioned, as far as I read his review, is that it's the best like SOTA model so far, and your tests even show this. So Reformer provide the best performance, but it seems that you put it at the very end and didn't pay much attention to it. Is it correct?
Yes, because my main aim was deeply investigate RavNet and only try to use different models to compare with it.
I don't get it because it seems that there is SOTA, and you try to play with not that prominent model. Why is that? Why didn't you get this best model and try do the same but with raw former?
I will plan to do it in my future researchers.
Okay, thank you.
Um, okay. Uh, First, like very borderline topic. I haven't found the notion, the definition of deepfake in your work. This is the first question.
I understand the definition of deepfake audios is the audios that produced not by human but by computer models.
Okay, how are you going to distinguish them? By data sets? Carefully prepared by we don't know who and for what reason. It could be like a well-known movie before the president election, and then all like make their choice. So maybe this data set was produced for pretty the same reason. And it's absolutely not about our deep understanding of what deepfake is. Uh, if that's all, so the second question is, have you tried your models on, let me say, generated like these deepfakes, so generated by you? We have a lot of models available on internet, so you can try to
I
generate.
understand. If I try to generate some deepfakes and test on my models, uh, unfortunately now it may be interesting for future. Thank you.
But as for me, it's like a very first what should come to your mind to try to test this model on uh, examples you can very simply generate and test. Why haven't you tried? Yes, just to check it really works. Not at a very, once again, very specifically completed by someone. We don't know the deep reasons why they do this and how they complete these data sets.
I understand. Thank you for your question. I will try to use it.
Okay. Okay, thank you.
Uliana, thank you for the presentation. Can you
Thank
go
you.
to page 17 with all the results? Mm, uh, it seems that this third data set, fake or real, clearly stands out. Very, very many models, very many models, the results you got are quite different for that particular data set. Do you have any idea why it is so?
Maybe because this data set may be collected in the wild with many real world scenarios, conditions, noises, and for this, it may be for this reason. But to say clearly, we should exactly deeply investigate the data set, the audio quality, the noises of these audios.
Uliana, many thanks for your nice presentation.
Thank you.
It provoked me to have a bunch of questions. I even looked into your thesis, and I have a page with your contents in front of myself. My general impression, and please correct me if I'm mistaken, is that the thesis suffers from several flaws. The first is inconclusiveness. The second is bias. And the third is opportunistic behavior. I would elaborate on that. So inconclusiveness, in my interpretation, means that the chapters do not have conclusions. For example, what's your coffee to go you took away from your related work chapter?
I understand.
What did you learn in there?
Uh,
This is the first. The second is then you presented data sets and evaluation metrics in chapter 3. Then you present your approach to solution, and then you straightforwardly go to experiments. Where is the presentation of your solution? Do you have any solution here? And this is just the further elaboration of Alexei's question about what is the contribution of this thesis.
but I have the chapter with proposed solutions to solve this problem.
I'm just reading the headlines, the headings of your chapters. Chapter 4, Approach to Solution. Chapter 5, Experiment.
Yes.
And where is the description of the solution? The approach to solution is the way you went until you got some solution.
I understand. Maybe I make mistake in the name of the chapter.
Yeah. So
And about
about
conclusions.
this was about the inconclusiveness, about bias.
I understand. Thank you for that.
Uh, I'm just looking at your results, and I have a very clear impression that there's one positive outlier here, and this one is a transformer, isn't it?
Yes.
Why didn't you take any other transformers to make a little bit more fair environment for their competition? To become a champion
Because
in your table. It was absolutely clear that Rowformer will be the champion here. Even before you started your experiments. Why did you organize your experiments like that? Where is the plan for your experiment in your thesis?
no, especially for me, it wasn't especially clearly to see that Reformer will be the best, especially in other data sets, other three data sets. And as we can see in fake or real, it isn't the best. Um, uh,
So without a doubt, it was not very clear for you just because you didn't analyze the related work in your chapter 2. So you didn't take any coffee to go after chapter 2.
no, I think that RAVNet model with 20 filters isn't so bad for in us with spoof data. It only differences in approximately 4%, and I couldn't say at the beginning of my researchers that it would show the best results on other data sets. Thus, I tried to investigate deeply, especially RAVNet, and unfortunately, in the end, I get such results. And
Hello, could you please recall us what was the publication date for the Rowformer? The publication date for the paper describing the Rowformer architecture and solution. The last column. You mentioned it somewhere in the slides. I mean, the paper. Yeah, 1. What's the date of the publication of your reference number 1? I can go
20,
in- I can go
2000.
to, it is 2019. 2019 means before the Christ in the settings. So why not looking more precisely at more recent publications on transformers in deepfake detection?
I can explain. This model was investigated in 2019, but in that time, that dataset as spoof 2021 wasn't realized, and they train their model on previous iteration of this dataset, and there wasn't showed results, especially for this new datasets realized by us for spoof. And then I couldn't tell that it would show the best results on the new data.
You know, unfortunately, and I'm sorry to say, this doesn't answer my question. Why you didn't look at the more recent publications on the other transformers used for deepfake detection?
As a transformers, there are a little, maybe only 2 or 3 transformers for this task.
As to the best of your knowledge.
As my knowledge, yes.
To the best. Okay, thank you very much.
I think we are done with the questions. Thank you, Ulan. And 1 moment. Yes. Go. So the next student defending her thesis will be Ludmila Potenko. She is supervised by Alexei Ignatenko, and the topic of her thesis is speech sentiment classification in a Ukrainian-Russian environment.
And present my thesis on topic speech sentiment classification in Ukrainian-Russian environment, which was supervised by Alexei Ignatenko, to whom I'm very grateful for support and guidance. The plan of today's talk is following. The first, I will discuss the background of my field and topic. Then I will define the project goal and review the data set which we were working during this project. Then I will discuss related works which will include the common challenges in the field and the promising approaches which we use to define our pipelines. Then we will discuss the result of our work, state the conclusion, and define the future works. In this thesis, we were working with emotion, a component of the human speech. According to American Psychological Association, emotion is a complex reaction pattern involving experimental, behavioral, and psychological elements. That means that the human emotion human emotion defines the behavior of the human, and it provides the feedback of how human reacts to the world. So studying and understanding and classifying human emotion may provide valuable feedback to various fields. For example, it may provide business value when we detect customers' emotion. Customers' emotion and classify them. The business might improve customer experience after knowing this information. It may be helpful for the mental health to, for example, detect depression during the calls to some medical institutes. Also, it may be useful by improving AI interface with humans. So when the emotion of the human is classified, AI interface may adapt to this emotion and change its behavior. So Paul Ekman defined 6 main human emotion, which is sadness, fear, disgust, anger, surprise, and happiness. So here we have joy, but it's happiness. Also, Russell and other stated that human emotion can be also depicted on the 3D Watt scale, which consisted of valence, which is sentiment, arousal, which is the strength of emotion, and dominance, which is how a human is taking control of its emotion. So those categorical emotions might be mapped to this Watt scale. For example, here we have anger, and anger has a high arousal and low valence. When sadness has also low valence, but also low arousal. In this thesis, we will work with valence dimension, which is sentiment of the emotion. Our project goal was set by Stream Telecom company, which provided us the data set we were working with. They aimed to us to develop the end-to-end system for conflict detection in conversation in a call center environment. In our thesis, as a first step to develop the system, we defined that conflict in the conversation happens when the main emotion of the conversation is negative. The sentiment of the conversation is negative. Also, after extensive search of relative literature for emotion recognition or sentiment classification in Ukrainian Russian environment for the speech, we found that there's very little results on it. So our sub-goal will be to evaluate and compare SOTA approaches specifically for Ukrainian Russian environment, I mean mix of the languages. So our data set is relatively small. It has a duration of 1 hour. It's recordings of the conversations in the call centers. It is carefully labeled by the Stream Telecom company itself. They provided us like audio files and text transcription. Also, they carefully removed some sensitive information from this data, like phone numbers and names, and added some preprocessing, like removing silence, dial tones, and so on. The average duration of the conversation is 50 seconds. It recorded in mono, one channel, and it was recorded in 8 kilohertz sample rate, which will cause us problems in the future. Also, the emotions which they labeled this data set into categorical emotions, which is anger, sadness, disgust, neutral, happiness, and surprise. And this distribution of the emotion was very unbalanced. We has mostly neutral and anger emotion. That's why we mapped them into sentiment scale. So we had, and after that, we merged positive emotions into neutral to have balanced data set for further binary classification. Also, we have imbalanced language component. We have like 2/3 Russian conversation and 1/3 of Ukrainian conversations. This is a example of the annotation. So we have the labeled transcription to each utterance, as well as the speaker, language, and the emotion. We don't have transcription for the time when they both speaking at the same time. So we reviewed the related works related to the field and defined some challenges and promising approaches, and we will start with the challenges. So the biggest challenge of the field, which is applicable for the all languages, but specifically for Ukrainian, is lack of data. We don't have research data set for Ukrainian language or the mix of Ukrainian and Russian. Therefore, we don't have the benchmark available. This happens because the high effort required for the annotation, because each utterances has to be like labeled by emotion, and mm, and sometimes, most of the time, that they also required to have the transcription. Another case is that it's hard to open data with uniform distribution, open data with uniform distribution of emotion sentiment. Therefore, the research data sets are often scripted and acted. Therefore, they may not be suited to the real world scenario because the emotion there are very, very pure. Okay, and also another challenge is emotion subjectivity. We need at least two people to assign the quality label. And the culture differences is that we may not use the data set, for example, in Hindi to Ukrainian, because the emotion, how they express emotion in Hindi may be different than in Ukrainian. So we defined three promising approaches to tackle our problem and define the speech sentiment classification system. The first one is a text-only model inspired by Wu and other. Second one is audio model. We will use handcrafted features and features extracted from self-supervised model, and bimodal fusion of acoustic and text component. So we will discuss those approaches in more details. So the first is text-only model. To this pipeline, we choose ISR model to extract transcription from audio, and the LLM model to classify sentiment. Also, we developed the second option for this baseline approach is to have the extracted features from LLM and the additional classifier model, so that we may equally compare all our baselines or our pipelines together. So the models we choose for this baseline is ISR. For the ISR, we choose Whisper Large V2, which provide us both transcription and translation, which we'll need for the LLM models. For LLM, we choose two English model, which were already trained to classify sentiment and emotions. And the third one is a multilingual model trained for neurolingual interface and is capable for zero-shot classifying. So this model supports Ukrainian language. And for the classifier, we choose logistic regression because our dataset is relatively small, and choosing the DNN model may caused us the overfitting on the features. So the pros of choosing the LLM is that they require no additional training on fine-tuning to use them right away, and they work both for Ukrainian and Russian at the same time. We don't need to create separate models for each of the language. And the drawbacks of these models of this approach is that we need to add additional ISR model, which will add additional error during transcription and translation, and it may cause some accuracy. Our accuracy will be down because of that. Also, this additional ISR model in our pipeline will increase computation time and computational requirement. Also, using text-only pipeline will not include the emotional component in audio. Therefore, it also may result in lower accuracy. The second approach is audio only model. It's simpler than the previous one. We directly use audio to extract features and pass the features to the classifier. The most interesting part is feature extraction. We choose two approaches to extract features. The first one, we choose the OpenSmile library to extract compare feature set from audio. The compare feature set provide us around 6,000 paralinguistic functional features. So the OpenSmile library extracts first the low-level descriptors from the speech, like some MFCC or a pitch and different audio features. Then it's applied the derivatives, first and second derivatives, and some statistical functions like mean, median, and so on. The pros of this approach is that it's language independent. It works for any language. But because we have so much features, and this compare data set also works for like music classification, and we might need to additionally select features which are really useful for us. Another approach is to use the model, WAF-to-WAC model, which is trained in a self-supervised way to like on the large amount of audio. It's trained to reconstruct masked audio. And it also supports Ukrainian language, which is like good for us, this XLSR model. And another process that it encodes both paralinguistic and linguistic information. So theoretically, we may not lose the component of the text. Yeah, but the main drawback of this model is that it's trained in 16 kilohertz sampling rate, and our data is trained in 8 kilohertz sampling rate. And we need to upscale our data, and it may lose in accuracy because our data has lower quality. Also, because of the domain shift, we may require fine-tuning to obtain the sufficient accuracy. And the features which we extract, like hidden states from the WAF-to-WAC model, are not explainable. The third approach is bimodal fusion. We choose two approaches to fuse our text and audio components. The first one is early fusion. It's just simple concatenation of audio and text features and passing them to classifier. And the second approach is late fusion, where we have two separate classifier model and we ensemble them together. So here are our experimental results. We evaluated our data set in using 5-fold cross-validation, and we reported accuracy, F1 score for the negative sentiment, as well as computation time for CPU and GPU for one audio data with duration 50 seconds. So what we can see from the results. The first is that English LLM provided the best result of 0.85 score. This is text-only model, and when we added compare features to this model using early fusion, we obtained like one increase in 1% accuracy. If we take the multilingual LLM, for which we used transcription in original languages, we can see that it resulted in 13% lower accuracy than English LLM. But this model was not specifically trained to classify sentiment. Also, we can see that compare features alone provided pretty good results, and it has the lowest CPU and GPU time. For CPU, it's very significant, but for GPU, it's not that significant, but still a few times faster. Also, WAF-to-WAC model provide lowest results, but we didn't tune it, so it's expectable. Also, we tried our model on a real world setup. The Stream Telecom company provided us with 3,000 raw audio files, and which were taken during COVID 2020. We applied some simple preprocessing by sampling and removed the silence and dual tone at the beginning of the each audio file. And we tried two models which we developed. The first one is a zero-shot classification for text-only model, and it resulted in 70 conflicts from 3,000 files. I manually reviewed those files, also 70 files, and I assigned some very much subjective labels to this. So in my subjective opinion, the 30 from 70 files were classified as really conflict or negative sentiment. And I choose 30 random files which were classified as negative, as positive sentiment, and all of them, for my opinion, didn't have any conflict. Another bias I found is that this English model has some bias according to COVID topic, because every true false positive case was related to the COVID, but not necessarily include the negative emotion of the speakers. Also, we tried acoustic model, and the acoustic model detected over 1,300 conflicts from 3,000 files. We tried both of them, compare and WAV2VAC, and these results show us a clear sign of overfitting on our clean data. So our clean data differ from the from the raw data, because raw data is noisy. It may include some dual tone, which was not unfortunately removed, some music in the waiting time, and some voicemails, which always classified as negative emotion. Also, troubleshooting is usually considered as a conflict or negative emotion, despite the fact that the sentiment of such conversation was rather neutral than negative. And also some edge cases, when some child is answering for their mom, or like a deep timbre of a man's voice, was also considered as a conflict. So the conclusion of our work is the following. The text-only pipeline showed pretty good results and is robust on real-world data. Also, we found that translation from Ukrainian and Russian into English is beneficial, despite the error it introduced by translation model. The audio-only pipeline using compare features has the fastest inference time, but is very sensitive to speaker change, noisy data, and recording setup, which results in overfitting. So to use this audio pipeline on real data, we need to create a bigger data set, more robust data set, and it will require a continuous retraining in a real-world scenario. The audio-only pipeline for WAV2VAC encodings, it theoretically should work very good on our data, because it was trained on real-world noisy data. But because of the domain shift and difference in sampling rate, we may need to fine-tune it to provide the better result. And by model fusion is showed the best result on the clean data, but to have it also to provide the good results on the real-world data, we must first sufficiently train the audio model before fusing it with text. So the future steps are the following. The first is increase the data set size. We may try data augmentation and pseudo labeling of this 3,000 data set, but we need definitely to include more people in label assignment. Especially, we need to review those labels with the Stream Telecom company. Also, we might try to train more complex models, like DNA, when we obtain more data. To try DNN models as classifier, we may try web-to-vec fine-tuning. And also, it was interesting to fine-tune LLM on our specific data to overcome such biases as we faced to the COVID. And also, there are also two interesting approaches. First one is to analyze on utterance level. So we analyze the whole sentiment of the conversation, but it's may be interesting to analyze how the sentiment changes during the conversation and assign the conflict label during this time after this time analysis. And also, it may be interesting to analyze in additional dimensions of the what, like arousal and dominance. So, and the finally contribution of my work are the following. The first is we develop speech sentiment classification system that may potentially add business value to Stream Telecom company by detecting conflicts and customer dissatisfaction during calls. And the second is that new researchers for speech emotion recognition, speech sentiment classification, on conflict detection for Ukrainian or mix of Ukrainian and Russian language may use this work as a starting point. Finally, I want to ask to thank Stream Telecom company for providing me opportunity to work on this interesting task. And thank you all for your time. And I'm happy to take the questions.
I can start. Igor? Yeah, that's not right.
Okay, thank you for your presentation. I have several questions. So can you go to the slide with the inference time comparison? Like you have for the compare model CPU time 2.4 seconds, and for GPU the same. But for the rest of the models, you have huge difference. Like, do you have any, like, how did you measure it? Did you convert your models to some open Reno or optimized it somehow? Or like, what is your understanding of this huge difference?
So first of all, I ran these experiments on Google Colab. For CPU, I used like the CPU high memory, and for GPU, I used L4 GPU. And according to Compare, regarding the Compare feature extraction, it works only on CPU with one thread. So we may not like anyhow to speed up it. So it may result only in these numbers. For the other, it's explainable because I didn't optimize the models in any way. I just run them on GPU. But for the ISR models, for the first two LLMs, and for the like 4 rows below, we may use a different whisper model, the optimized one, to speed up it even further.
Okay, thank you. You could you please, like, maybe I missed it, but like for me, if you have a large language model that is English and you translate first Ukrainian or Russian to English and then to do this, could you, like maybe you could just use not like multi-language, but specified for specific like Cyrillic or Russian, Ukrainian, like for me it's hard to understand why translation giving like improvement for this and what's the reason like behind this? What do you think?
Yeah, I think that it's mostly because these models were trained specifically for sentiment classification or emotion classification. So it's like the main goal of this model is to classify the sentiment. And for the multilingual, it's a zero-shot classification, and that's why we don't have such a improvement in the accuracy. But I didn't find LLM for the Ukrainian, and I find the LLM for sentiment classification in Ukrainian and in Russian. But if I try it with my mixed language data set, they provide lower results.
Okay, so but you didn't train the model. You trained just logistic regression on top of it. Okay, got it. Thank you.
I will be quick. Thank you, Ludmila. Can you switch to slide number 6, please? So the whole duration of data set is 1 hour, but as far as we understand, there are chunks of these audio files recorded. So what are the lengths, duration of this separate conversation audio files?
The total payload is 35 minutes.
Total, but I mean like every 50 seconds? Okay, average.
For the each utterance, I'm not sure, but it's like 10 seconds, I guess.
And then when you show on the result table, the duration time is training for the whole 1 hour data set.
No, it's for one audio file with duration 50 seconds.
Okay, so to get the results for 50 seconds, we need to spend computation time like 2 minutes. Okay, I see. Can you get back to this slide number 6 again? There is certainly unbalanced data, right? So we have far less positive records. How do you deal with this? Do you balance your data set somehow?
So for the our main goal to detect like conflicts, it doesn't matter where the sentiment is positive or neutral. It's important to detect a negative sentiment. So
Okay,
to balance, we just merged the
makes
sentiment.
sense. And how do you label your data in terms of? You showed us on the one of the slides the labels of yes, this one. Was it was provided by? Okay, I see. That's it. Thank you.
So thank you very much for your nice presentation. Just waiting until they go away. Just to eliminate the white noise on the record. Yeah. Again, I was looking into a thesis. Sorry about that. What I found there is a couple of things. Well, my first concern is about the order of the chapters. So you start with the introduction to related works, which is perfectly fine, and I'm on the same page with you. And then you describe your data sets, and out of a sudden evaluation, judging by the title of the chapter. And then you go to the methodology after having described the evaluation already. And only after that to go to the experiments, which are the essence of evaluation. Could you please comment on that?
I defined how the data will be evaluated mostly after the literature review. So after I review the related works, I understand how the such task is evaluated in the field, and also it's related to the data set. How we will be evaluating this, because if we have this classification task, we use accuracy and F1 score. But if we would use the VAT dimension, if we would have this continuous numbers, then we need to choose the different evaluation metrics. That's why I put the evaluation in the data set.
So they mean that your chapter data sets and evaluation just presented your evaluation plan. Okay. What I missed then there in this chapter is the objectives of your evaluation. Because you do not evaluate data sets. Normally people do evaluate solutions that somehow use these data sets. And there was nothing said so far except the related work. What will be the solution in your thesis? Do you have any contributed solution?
The solution are all three pipelines I developed. And
Where can I see these three pipelines in your thesis?
so the pipelines are inside the methodology.
Wow.
Under, yes, sorry about that. They are under methodology, and they.
So this work is not in computer science; it's in methodology.
No.
But your structure and what you're saying right now in answering my question suggests this conclusion.
I'm not sure I really following your question, because we developed three pipelines, and which of one has different properties, and it's up to Stream Telecom company to choose the best. But like on the current stage, I would recommend to use the text only LLM, while we combine more data together to train acoustic and bimodal fusion. And in the final stage, the bimodal fusion would be the best pipeline. And when we train acoustic model properly.
This is excellent, but this is somewhat undercovered in your thesis. One more thing. Going back to the evaluation planning, could you please go forward to slide number 17, I believe, with the evaluation results? You mentioned fivefold evaluation here. Why fivefold?
Because we have a relatively small data set, and we want to use all of it for provide evaluation metric. And why 5? It's mostly inspired by the related works, because EMOCAP, the data set, which is the most popular data set.
No, but the related work doesn't do not use your data set.
Yeah, sure.
So blindly
yes.
taking a recommendation from related work without any analysis of the related work does not fly, and you do not have the analysis of the related work in your chapter 2, sorry to say. Okay. One more question. I'm looking at your columns number 3 ACC and number 4 F1, and I would like you to explain those stupids like myself. What's the difference between ACC and F1?
Well, F1 score is like a harmonic mean of recall and precision, and in our case, it's important to specifically
balanced F1, yeah?
Yeah.
Okay.
And it's important to for us in our case, it's important to use F1 score as a main metric, because we more interesting to correctly classify the conflicts in the text than the not conflict. We are more interested in to have more conflicts classified as conflict than not conflicts classified as conflicts, like
Yeah, I mean false negatives and false positives.
Yes.
I'm asking you about the slightly different thing. I'm asking you about the difference in the measures and the reason you used both here. And my inspiration to pose this question is just the comparison of the values in the table. In your table, the values are just the same, both for ACC and F1. The only difference is that F1 is a normalized ACC. So why using both? What is the difference? I mean, in the sense of the measure.
Yeah, so for this particular slide, I believe it's my mistake to report them both. But in Thesis, different models may provide different results. So the model may provide high accuracy but very low F1 score. But those models are not reported there on this slide because they really bad and we
Okay.
don't want to review them.
Thank you. I'm done.
Okay, your task come from the company. Have you implemented the results and have you some feedback on it?
We delivered only text-only pipeline, the inference pipeline yet, and the Stream Telecom company was happy with this solution so far, but for acoustic and bimodal, we do not yet deliver them. And we will discuss if we need to do this before we train them properly on the larger data set, because it may not make sense really.
But do you have some document supporting your words?
I don't.
Okay, thank you.
Thank you, Ludmila, for your presentation. You mentioned that translation the text into English improves the performance of your pipelines. Can it be the reason that you is it can you actually use better models for Ukrainian or Russian text to improve these?
Yes, it's theoretically possible, but we don't, at least during my search, I didn't find those models which will be trained for sentiment classification and may improve our result. But it's possible, and we may avoid the translation. Yeah.
Thank you for your presentation. I have also a couple of questions. So I'm curious, how was you maybe investigated that how does the possibility of classification sentiment drops if we do the translation? For example, my understanding is that the text, like voice and audio, should contain more features, as you mentioned, like tone of voice and stuff like that. And when we translate it to text, does the text always capture all of these features? And for example, is using the text, what is the potential highest accuracy and F1 score for the test? Is it also 100% or maybe lower?
Oh, sorry, I didn't get your question. So you're asking if using the same model on the transcription, original and English will have some difference?
No, let's assume we have audio file and it has been classified as positive or neutral. And when we do the translation audio to text, does this fraction of like possibility by the model to capture the positive and negative holds, or is it somehow distorted because we do this translation and we lose some features?
It's didn't I didn't do the research for this, but from my review of the translation text, I can see that the words which capture the emotion, negative or positive, they are mostly they are almost always translated because they are simple. They are usually clearly said. and that's why we don't lose this during translation. But if we the most the words which suffers most are some specific words related to terminology or something like this, because Whisper like capture them directly, like not directly, and the translation part is trying to match it to some word in English, and this may add some confusion. But the emotional words, it's captured correctly.
I got you. Thank you. And the next question is about imbalanced data set. And so you have like two axes of diversity. You have negative positive class and you have Ukrainian and Russian language. And if you combine these two, you will get approximate, if you kind of don't pay attention to the language, just to the sentiment, you can roughly get balance, right? Approximately, let's say 50%. But have you maybe checked the matrix per language, not only per sentiment?
No, unfortunately, I didn't do this, but it's worth investigating in the future work.
Okay, thank you. And the final question is about, so we already a little bit touched this, that as far as I understand, the main goal of the company is to make its customers happy, and they want to catch most of the negative conversations to find out the conflicts and so on, such that they could resolve it. And I'm curious whether you maybe tried kind of a threshold tuning. What threshold for the logistic regression you choose? Is it 0.5, or maybe you tried somehow tune it?
So I tried directly, this approach I tried directly with a zero-shot LLM classification. So I extracted the probability of zero-shot labels and tried to fine-tune it using different thresholds, but it didn't really provide any improvements. And for the logistic regression, I didn't use such approach.
Okay, thank you. We have a question from the audience.
Yeah, thank you for your presentation. Okay, let's start from evaluation section. So just addressing also the previous sections. You are solving the multi-class task. Am I correct? Yeah.
It's binary classification.
Oh, okay. Yeah. So I'm just curious why you have chosen like only metrics with hard classes, not using some like widely used rock oak metric, which is threshold independent.
Well, I believe mostly because those metrics which I used is easier to explain to our customers. But yeah, that's a good point, and it's missed on my side.
Yeah, and like just following the previous question, so the thresholds are set to 0.5, or you just take the highest probability from a logistic regression?
I choose the highest probability.
Okay. Can we go back to the dataset section? Cool. Can you please explain what is sample rate and in which points we measure sample rate?
So the sample rate defines the quality of our audio. So we like taking samples of the audio, I believe amplitude for 1 second, 8,000 times in this case. And that's why we have like 8,000 samples. And if we compare it to 16 kilohertz audio, it has like twice more samples and it can capture more information, and the quality of the voices will be better.
Okay, but you measure it in hertz, so it's like kind of frequency measurement, not like just number of points. I'm just addressing that if if you take a look at Nyquist Shannon theorem, so there is like dependency between like the maximum frequencies that you can have in your audio and the sample rate, and we need just to clarify that these are like two separate points. So when you say that you have like 8K points in your in 1 second, it means that your sample rate that your maximum frequency is twice lower. So your like maximum frequency is 4K kilohertz, and in your particular example, the sample rate, I guess it's like you have like 16K points in 1 second or 8K points in second.
Well, actually, I used the just like common metric, which were returned by Librosa library. I didn't really dive deep into this sampling rate metrics.
Okay, and what you defined in like what you defined in this Librosa sample rate parameter, 8K or 16K?
S- So really, I don't know how to answer this. I didn't fully capture the essence of the question. How it impacts the thesis, the results.
Yeah, it's impact because in your conclusions you say that it may be important to retrain wave to back with with appropriate sample rate. So like and if you use like some models like wave to back or whisper, they also trained on some particular sample rate, so they have standardized sample rate. And I think we can go to the next question. So what do you think is it sorry okay what do you think is it critical to decrease or increase sample rate?
Well, it's better to increase sample rate to obtain more quality audio, and therefore it can like match the sample rate in which model were trained. But as far as I understand, 8 kilohertz sampling rate is a standard for phone calls conversation, and therefore I'm not sure if it's really feasible to sample in this more
But
quality data.
but I mean, like when you resample, when you have like some 8K kilohertz audio, and is it okay to resample it to higher sample rate or to lower sample rate?
So to actually feed to the model, we need to resample it to higher, not to the lower the audio. And that's in this case, we will retrain like the fine-tuned model to on this lower quality rate. We cannot use 8 kilohertz directly because it will be like squished, and the web-to-web model will still like comprehend it in 16 kilohertz despite it 8 kilohertz.
Okay, I see. Thank you.
Thank you, Ludmila. So unfortunately, we were over we are 20 minutes late. So for the next speakers, I really encourage you to stick to the schedule. And if you will be over 25 minutes, I will stop you. So because we have active discussions. So and we have 10 minutes break.